In this last video for lesson 6.1, we're going to talk about different factors that impact confidence intervals. So it really is the margin of error that controls the size of your confidence interval, because the margin of error is the value that you add and subtract. The margin of error is controlled by two main things, the Z star value as well as N. So we're going to talk about both, the confidence and the sample size, and how they impact your confidence interval. To start with the visualization, if you go back to the activity and amplify, there's just a couple visualizations where you can actually try it for yourself. As you change the value that corresponds to um, the Z star, like your multiple of the standard deviations that you are away from the mean, you can see how it impacts your percent. So that if you want to have a high confidence, like 95%, look how big the purple range is, compared to if you have a lower confidence, like only 65%. As you increase how confident you want to be, like if you want to be almost 100% confident, how does that purple area change? Does it get more narrow or get more wide? So this would be like 100% confidence versus only about 50% confident. Think about if the width gets bigger or smaller. You can choose what option it corresponds to and explain your thinking. That's what we're going to talk about next to see if you got that answer correct. So the confidence level determines your Z star value. So how confident you want to be determines how wide your margin of error is. If you want to be very confident, like if you want to be 99% confident, it will make your interval more wide. So if that's what you said, that the width of the interval increases, if you want to be like 100% confident, the purple region takes up all the area under the curve almost. But if you want to be less confident, then the purple region gets smaller. So the more percent confident you want to be, the more wide your interval gets. The problem with a wide interval is then your range gets way bigger. So if you want to be 99.9% sure, you would say that the percent would be between about 45 and 67. That's a pretty big range. Whereas if you don't need to be as sure, like if you only need to be 50% sure, the range is only between about 54 and 58, only about 4% different. So the higher percent sure you want to be, your interval gets more wide, but then because it's so wide, it's not as precise because you have a really big distance between the lower and the upper bound. On the other hand, if you're less confident, then the interval gets more narrow, the purple range isn't as big, and you'll be more accurate. What more accurate means is that there's not as much distance or not as much difference between the upper and the lower bound here. This table kind of summarizes the confidence level versus the width of the interval and how sure you can be. But to show you that this is also true with numbers, for our summary bylaw example, let's compare a 95% confidence interval to a 99% confidence interval. Technically, we already did this work for the 95% confidence interval, so if you want, you could just copy that over from the last video. Make sure you can just get the numbers. Here was our proportion, sample size, the formula for the standard error, the formula for the margin of error, formula for the lower bound, and formula for the upper bound. You can pause the video anywhere or rewind it in there if you need any of those formulas again. If you want the 99% confidence interval instead, you will have to recalculate the margin of error since the margin of error does depend on that percent confidence. The standard error doesn't change, and for the sample size, we also don't change it. For our lower bound, we subtract our new margin of error, and for our upper bound, we add our new margin of error to our p hat. So for 95% confident, we were between 51.7 and 60.3 approximately. To be 99% confident, it changes the bounds to be between about 50.3 and 61.6. So as you can see here, if you want to be more confident, go up to 99% confident, this interval will be wider. Not that much wider, but we go from 51.7 to about 50.4, so more than one lower. And on the upper end, we go more than one up. So it makes it about 2% plus wider. This means you have less precision, or you can call it accuracy. We lost precision because our confidence level got higher. And you can see that with the numbers. The lower bound is lower, the upper bound is higher. That means the interval is wider and you're less sure of what the population value is. Not only does the confidence interval depend on the confidence level or your Z star, it also depends on the sample size. You can go back into the amplify activity to show you how the sample size changes the interval. These are our exact numbers for the summary bylaw example. We start with 516 people, but if you asked fewer people, look how the confidence interval changes. Is that more wide or more narrow? If you ask more people, like 1,000 people, look at how the purple area and the width of the interval between 54.4 and 57.6 changes. The number of people you ask does change the confidence interval, both the upper and the lower bound, and how you envision it in terms of the shaded area of the curve. If I go back to my original amount of 516, there it was. Oh, there we go. It shows me the interval was between 53.8 and 58.2 people with 68% confidence. You can scroll ahead one more and say, as you see the sample size getting bigger, what happens to the width of the interval? So look at the width here, 53.8 to 58.19. If you make the interval wider, what happens to the lower and the upper bound? Is the width higher? Is it lower? Or does it stay the same? Tell me what you think, and that's going to be what we talk about in Excel next. So the sample size is related to our width of the confidence interval, and it's actually has the opposite effect, that when you increase sample size, the confidence interval actually gets more narrow. They're opposites of each other. The reason that they're opposites of each other is because n is in the denominator of the fraction. If you take this formula for the margin of error and you solve it for n, so you rearrange the equation to get n instead, n is opposite of the margin of error, and the margin of error tells you how wide the interval is going to be. So if you get more people in your sample, if you ask more people, then your margin of error will go down. They are opposites of each other. So one way you can get an interval that's more precise and still keep a high level of confidence, like 95% or 99%, is by asking more people to be in your sample. How do you know you have enough people in your sample? Well, before you take the sample, you can actually calculate how many people you need to ask in order to get a certain level of confidence using this exact formula. N will be the sample size you solve for. Z star is the critical value. The critical value is determined by the level of confidence. So if you want to be 95% confident, you can calculate what the Z star value will be in Excel using this formula. I'll show you how to use it when we do the calculations next. P hat will be the sample proportion that needs to be given to you, and ME is the margin of error that's also given to you. Let's look at an example of how you would calculate the sample size you need for the Sudbury bylaw example. So let's say Sudbury wants to estimate to within 5% the portion of voters who will vote in the next election with 95% confidence. In the previous sample, they got 289 out of 516. That was our sample proportion. For the margin of error, that's usually given as a plus minus in the question. In this question, they say they want to be within 5%, so that's the margin of error, 5%. For the confidence level, they want to be 95% confident. We use that 95% confident to find Z star with this formula. You have to do norm.s.in, where the probability should be your confidence level divided by 2 plus a half. So this will be your Z star value. For 95% confident, it's approximately 2. That's why in the empirical rule, we said 2 standard errors or 2 standard deviations is for 95% confidence. It's not exactly 2, but it's close. I want to draw you a quick picture for why we have to take the confidence level divided by 2 plus 0.5. If your confidence level is 95%, let's say, Excel is trying to find you this value for Z star. The Z score that will give you 95% in this middle area. The problem is Excel can't do middle areas. It always does less than. What I mean by that is it needs this area here. So how you can find the entire area in yellow quite simply is if you divide the 95 by 2, half of it will be on this side, half of it will be on this side. So if I do 95 divided by 2, let's say I get this area here, from the Z star to the middle. Then 0.5 is the other half of the whole curve, because under the whole curve is 1. So half of it would be 0.5, this area in blue. So if I take the confidence level and divide it by 2, that's the green area on the right side. The 0.5 is the blue area on the left side. Together they add to the whole yellow area, everything less than Z star. So if you follow that format, that's how you'll always get the Z star value. Finally, to calculate n, you literally just have to use the formula. Z star divided by me to the power of 2 times p hat times 1 minus p hat. But because n is a number of people, you should always round it, and you should always round it up. To force Excel to round up instead of rounding to the nearest value, you use the function called ceiling in Excel. Ceiling makes you round up. Whoops. Sorry, I chose the wrong one. Use ceiling.math with just the number, and it will round it up to 379. So if you want to be 95% confident and have your margin of error to be within 5% on the lower and the upper side, you'll need to have at least 379 people in your sample. So that tells you how many people to ask if you're actually going to go out and do this sample. One other thing you have to consider is it is possible that you won't have an estimate based on a previous study. What I mean by that is in this question, it says the previous year's sample was 289 out of 516. But if you're just trying to go do a sample for the very first time on a question you've never asked before, if you've never asked the question, you don't know what percent of people are going to say yes and what percent of people are going to say no. Another way of saying that is you don't know the sample proportion usually until you already do the sample. So how can you calculate n before you do the sample and before you get the sample proportion p hat? What statisticians do in this case is if they really have no idea what the p hat value is, they use a value of 0.5. The reason they use a value of 0.5 is if you look in this calculation that involves p hat times 1 minus p hat, the biggest that number can be is when p hat is 0.5. Every other number smaller than that gives a slightly smaller answer. So basically, the worst case scenario, or what requires you to ask the most people, is when p hat is 0.5. So if you really don't have an idea of what p hat is, the default rule is to use 0.5. Let me show you an example of that. This one says, suppose a mobile phone company wants to determine the current percentage of customers who use text messages on their cell phones. How many customers should they survey to be 90% confident with a margin of error of 3%? This one says nothing about how many customers or the percentage of them use text messages on their cell phones. They just don't know. So when you don't know, you use a value of 50%. The margin of error is 3%. The confidence level is 90% confident. To calculate Z star, you use norm.s.inv to give the Z score. And for the probability, you do the confidence level divided by 2 plus 0.5. That gives me my Z star value, which is about 1.64. Once I have all those numbers, I can use this formula to find N. I take my Z, divide by my margin of error, and square that, then multiply by P, and multiply by 1 minus P. That should give me 751.5 people, but if I round that up using the function called ceiling that always rounds up, I get that I'd have to ask 752 people in order to meet these conditions for being 90% confident with a margin of error of 3% when I don't have any idea for what the proportion p hat is. I'll show you one more example of calculating sample size. This one says, suppose an internet marketing company wants to determine the current percentage of customers who click on ads on their smartphones. How many customers should the company survey in order to be 90% confident that the estimated proportion is within 5 percentage points of the true population proportion? So again, the only numbers we have in this question is we want to be 90% confident and within 5 percentage points for the margin of error. That's what this within 5 percentage point means. It's the margin of error value. With the confidence level, you can calculate the Z star value from the normal distribution. I take my confidence level, cut it in half, and add 50%. Then, to calculate my p hat value, it's not given in the question. We're not given any estimate of how many customers currently click on ads on their smartphones. So if you have no idea what the value is from the sample, the worst case scenario is to use p hat of 0.5. That will give you the largest number of people that should be included in the sample. Once you have those values, we use our formula. Our formula for N says you take Z star, divide it by the margin of error, and square that value. Finally, multiply by your sample proportion times 1 minus the sample proportion. This gives a decimal, 270.55. We cannot ask a fraction number of people. It has to be a whole number. So we round up using ceiling and get that you must ask 271 people on this survey in order to be 90% confident and within a margin of error of 5 percentage points. So both the confidence level and the sample size influence how big your interval is. For the confidence level, the more confident you want to be, it will make your interval wider and less precise. If you want to maintain a high confidence level without giving up precision, one way is to ask more people. And before you conduct a sample, you can always get an estimate of how many people you should ask using this formula for N, the sample size, which you can calculate both if you have a previous estimate for the sample proportion or using 0.5 if you have no previous estimate. This is the last video for calculations for confidence intervals for the sample proportion. In the next lesson, we will look at confidence interval calculations for the mean.